This is the MATH201 midterm exam review. There's actually an assignment where you have a bunch of problems that will prepare you for the midterm exam. And I'm going to work through all these problems probably fairly quickly since this should be a review. But the idea of doing this is, as you're doing these problems, if you happen to get stuck or aren't quite sure how to work them out, you can refer to these videos and it might help you to understand how to solve the problem. So I actually printed out all these problems. They're going to look very similar to yours. I assume different numbers, but similar kinds of problems. And I have the key also, since I'm the instructor. I want to do that because as I work these problems out, I want to check and make sure my answers are correct, because nothing's probably worse than working out a problem on a video and then doing something incorrect and not catching it till after the fact. So I will be checking the answers to make sure I did not make any mistakes. So let's jump in. So here I will show you the first problem. If possible, I will probably try and work the problems out on this paper, but in some cases, there's probably not enough room. So here we're given this function g of x equals x squared minus 9, and they asked us to find a bunch of, this is really like what I call a function notation problem. It's really understanding functions. They want to find g of -7, g of 0, g of 7, g of a plus h, and then this thing here, which is actually called the difference quotient. It's a pretty something we use in calculus to find the derivative. So this is really more of a function notation problem, not really a calculus problem per se. So let's go ahead and do this. So the first one they say is g of -7. So right, function notation says g of -7 means you put a -7 into your function every place there's an x, right? So if I plug in -7 for x, it becomes -7 squared minus 9. 49 minus 9 should be 40. G of 0, now I plug in 0 for x. We can sort of just do this without even writing anything down. I plug in 0 for x, 0 minus 9 should be minus 9. G of 7, it's interesting, g of 7, up here I did g of -7. If I put a 7 in here, since it gets squared, it's going to be 49 again. 49 minus 9 is 40. So it's interesting how g of -7, g of 7 give the same result. Now it gets a little more interesting. Now we're going to plug in for x, a plus h. So gonna have to do a little algebra here. So once again, every place there's an x, I'm going to put in a plus h. So x squared becomes a plus h squared minus 9. Now what they normally want you to do is they want you to go ahead and multiply out these parentheses. And once again, I'm going to skip a few steps here and hope I don't make mistakes, but a plus h squared should be a squared plus 2ah plus h squared. Then you still have the minus 9. So that actually should be the answer. Now this last one, it's interesting how here they ask for a plus h. Look at the first part of this, x plus h. So it's almost the same thing, except instead of a, they have an x. So what I'm going to do, instead of redoing all this, I'm going to take this answer and every place there's an a, put an x, just to save time. So this g of x plus h is going to be x squared plus 2xh plus h squared minus 9. So this right here is g of x plus h. I could have done it the long way. I could have put in x plus h squared, but since I've already done it, I could save some time. Then minus g of x. So then you subtract. Now it's important that you put both these in parentheses, because if not, you'll probably make a math error. So minus g of x, right? There's g of x, it's just the original function. And then the whole thing, all of that is over h. So now we have some simplifying to do. And normally if you do this difference quotient correctly, some stuff is going to cancel out. First thing I want you to realize is when you subtract this whole parenthesis, this minus sign gets applied to both things in here. So in effect, I'm going to sort of get rid of these parentheses. And when I do, I'm going to end up with minus x squared plus 9. So it's almost like it's this parenthesis minus x squared plus 9, right? So if you look at, I got an x squared here and a minus x squared. So those, when you add them together, equal 0, that cancel out. I've got a negative 9 and a 9. Those cancel out. So what you're left with, if I can make room here, is 2xh plus h squared over h. 2xh plus h squared over h. Now, once again, hopefully you remember your algebra, you realize I have an h in both terms in the top, h in the bottom. So this cancels, and one of these cancels. And you're left with 2x plus h. And that should be the answer for this last part. So that was really a function notation problem, although this difference quotient is the thing we actually end up using in calculus. All right, number 2. So here they give us a graph. You can see this here. Looks like a normal parabola, except you notice here they have an empty dot. You know, in graphing, an empty circle means the graph doesn't exist there. It's like a gap, right? So it's a normal looking graph, except there's like a break or a gap here. So now this is a limit problem, looking at a graph. Decide from the graph whether a limit exists. If a limit exists, find its value. So they're saying, what's the limit of this function? The limit of this function represented as a graph. What's the limit as x approaches 3? So with the graph, what you do with the limit, you find x3 is right here. So to find a limit, what you do is you approach the value of x from the left and you approach it from the right, and you see what the function approaches. So in other words, if I go from the left, it's like I move along the graph until I get almost to the value of 3. So from the left, the function approaches 4. Now, if I approach x equals 3 from the right, the function is 4. If both sides approach the same value of the function, then you have a limit, and that is actually the limit of the function. So since both sides of this are approaching a value of 4, then the answer is the limit is 4. So the idea about a limit is, even though if someone were to say just for fun, what is f of 4? What this means is, what's the value of the function when, oops, I meant to say 3. What's the value of the function when x is equal to 3? For that answer, it's actually undefined because the function doesn't exist there. But if they ask you what the limit is as x approaches 3, the limit is 4. So the limit does exist even if the function at that exact point doesn't exist. So that's one interesting aspect of limits. Okay, number 3, it looks like another limit problem where they give us a graph. So this is like a little different. It's like a straight line, linear, and then a point here, and then the graph jumps down here and then starts going up again. So it almost looks like a piecewise kind of graph. So they're calling this function g. So here's what they're asking. They're saying, what's the limit of this function g as x approaches 2? Now that little plus means as x approaches 2 from the right side. Sometimes we think of this side of the graph as like the positive x-axis, and over here on the left is the negative x-axis. So when they have the positive here, they're saying approach it from the positive side. So it's almost like, let's go find, we're looking where x is 2. When I was doing this problem before, I was looking here, but that's not here. X is 2 is right here. So we're looking at this value right here. And it says, so the limit means as you move along the function, as x gets closer and closer to 2 from the right-hand side, what is the function approaching? Well, it's pretty clear, right? As x gets closer and closer to 2, the function is 0, right? Because it's this point right here. So the function does exist, and it's actually 0. Just for fun, just to make sure you understand, what if they had said, what's the limit? Here's sort of an interesting problem. What if they said, what's the limit as x approaches 1? Well, here as x approaches 1, you have to go from both sides. So from the left side, it would be 4. From the right side, it would be -2, right? Because x equals 1 is right here. Well, from the left and the right, they're approaching different values of the function. So you would say, actually, function, the limit doesn't exist as x approaches 1. But up here, they're saying x is approaching 2, and they're telling us to look from the right-hand side. It's interesting. What do you think the answer to this would have been? The limit as x approaches 2 of g of x. Well, that means you have to approach x equals 2 from the right and the left, but they're actually approaching the same point, so that would also be 0. All right, I'm giving you some extra problems free of charge, but anyways. All right, so those are the first, 3 problems. Let's go to number 4. Now, number 4 is a problem because I printed it out. When we look at the question, the first part of it is a multiple choice. It's supposed to be 4 graphs here, but I was only able to print out the first 2. And I think the correct answer is not actually here. So let's look at the problem, and I'll try and draw the graph for you and show you what's going on. Graph the function and then find the specified limits. When necessary, state that the limit does not exist. So here is my function. Make it clear. Here's my function, and then here are like the questions for the problem. So it may not be very clear. So here's my function, and this is called a piecewise function. It means it has 2 parts to it. So when x is less than 4, the function, this is the function. But when x is greater than or equal to 4, this is the function. Now, since we don't have the graph here, let me go ahead and quickly sketch this graph. It's not too hard to see what it would look like, because neither of these are correct. So this won't be perfect, but I'll try to. So this is my function. The vertical axis, the horizontal axis is my x. So everything, it changes at 4. So here's the transition where it's going to change. Now to the left of 4, when x is less than 4, the function is 4x minus 10. Now the easiest way I'm going to do this, this is going to be both of these are actually straight lines. But this one, I'm going to plug in, let me plug in when x is 3 and I plug it in here, 3 times 4 is 12, 12 minus. When x is 3, it looks like the function is around 2. Now when x is 2, looks like the function is minus 2. So I do that because if I can get 2 points, I can sort of draw this line. Now for this graph, if x would ever happen to be 4, it's actually 6. 1, 2, 3, 4. So if I go up here, when x is 4, it's going to be 6. But you notice since it's x less than 4, I have to do like a circle here, because x cannot equal 4 from the left side. Now, when it's greater than 4, the function equals x. That's pretty simple because if I do like at 4, it's going to be 4. At 5, it's going to be 5. So here's what this graph looks like. To the left of 4, it's this straight line. To the right of 4, it's this one. And you can see there's a gap when x is 4. So now let's answer these questions. What's the limit as x approaches 4 from the left side? So as I go up here, as x approaches 4, I already said, looks like it's going to be 6. Now they say, what's the limit as x approaches 4 from the positive side or from the right side? So you come this way as x approaches 4. The function is 4. So the limit as x approaches 4 from the positive side is 4. And then they finally say, now what's the limit as x approaches 4? So here you're doing it left side only, here right side only. Here, this means you have to compare the left and the right. And if they approach the same value, that's the limit. But you notice when x is 4, the two sides don't approach the same value. The left side approaches 6, the right side approaches 4, so therefore the limit doesn't exist. Makes sense, right? There's like a gap here. All right, so that's some problems looking at limits from graphs. Now we actually look at limits just mathematically. So for instance, we have use the theorem of limits. So here's about a bunch of math words, but we're going to talk about just how to actually solve this problem. When you want to solve a limit problem mathematically, what I taught you guys was the first attempt is you simply, whatever the limit's approaching, you plug it in for x, and then you see what happens. So let's plug in -2 for x, -2 squared minus 6. -2 squared is 4, 4 minus 6 is -2. If when you do this, this thing equals a number, then you're done. That's your answer. Right? Very straightforward, not very hard. Now, this doesn't always happen. It doesn't always equal a number, but if it does equal a number, then you're done. And that's, here's another one. Same instructions, now with a limit as x approaches 3 of x squared minus 9 over x minus 3. First step's always the same. I'm going to plug in 3 for x and see what happens. So you got 3 squared minus 9 over 3 minus 3. So 3 squared minus 9 is 9 minus 9. You get 0 on the top, 3 minus 3, 0 on the bottom. Now this is a special situation. This happens sometimes where the top equals 0 and the bottom equals 0. Now normally what you do in this case is you go back to the original problem and you try something, and oftentimes this works. What I'm going to do is, in these kinds of problems, a lot of times if you go back and you look at the top by itself and try and factor it, and look at the bottom by itself and try and factor it, then oftentimes you can actually find the limit. So I changed pins. It's hard to see sometimes. So now let's see if the top factors. X squared minus 9 is what we call difference of squares. Hopefully you guys all remember how to factor. Factors into x plus 3 times x minus 3. But the denominator is just doesn't factor x minus 3. But what's interesting now is I've got identical parentheses in the top and the bottom. I can cancel those. So once I do that, now my problem becomes the limit as x approaches 3 of x plus 3. Now I go back and I treat this like a limit problem, right? Where the first step is you plug in 3 for x and see what happens. And when you do that, you have 3 plus 3, which equals 6. And that's going to be, whoops, that's going to be your answer. All right. So you got to keep those straight, right? The first limit problem we did, mathematical limit problem, when you plugged in the number for x, just equal to number, we were done. However, this one, when we plugged in the number for x, we got 0 over 0. In that case, we tried to factor and cancel and did it again. And then we did get an answer here. Now it looks like we're back to a number 7, another graphing problem. Use a graph to answer these questions. So now it's like 2 questions in the same problem. So this looks like another one of these, looks like almost like a piecewise function, right? It's 2 sort of different graphs. Looks like here at x equals 4 is like the transition when things change. You notice it's a closed circle here and an open circle here. First thing, what is the limit of the function as x approaches 4 from the positive side? So from the positive side, you head this way. As x approaches 4, what does it equal? I think this is 1, 2, 3, 4, 5, 6. Looks like 7. So first answer is 7. Now the limit as x approaches 4 from the negative side. So now I'm moving like this toward x equals 4. This is going to be 1, 2, 3, 4. Should come from the left side. The function is going to equal 4 as x approaches 4 from the left side. Then part B says, so what's the limit of the function when x approaches 4? Well, the way you find the limit of the function is you look at what happens when you approach it from the left and the right. If they approach the same value for the function, you've got a limit. But in this case, you can look at the graph or look at the numbers. They're not approaching the same function. So you say It doesn't exist, right? Which makes sense. You can't have the limit at a place where there's like a big gap or a break. And then now they ask a question, is f continuous at x equals 4? Why or why not? Continuous means one way to define continuity for a graph is, can you retrace the whole graph without ever lifting your pen off the paper? In other words, is the graph always connected? Well, look at, if I go along here, if I want to keep tracing the graph, what I have to do, I have to jump up, lift my pen off the paper, and then keep tracing. So obviously, this is not continuous when x is 4. There's a big gap here. So, oh, I forgot the answer part. Okay, I've jumped ahead. So C is a limit doesn't exist. Select the correct choice below and fill in the answer. Okay, I skipped part C. Sorry. All right here, sorry. They're saying, what is f of 4? F of 4 is, you go to the graph, you look at x equals 4, and you say, what does the function equal? Well, x is 4 is right here. You see here, it's an empty dot, so the function doesn't exist here. Up here, it's closed. So the function, when x is 4, the function actually equals 7. Sorry, I skipped that. Whoa, down here it's 7. Now, when they say, we answer this question, whether it's continuous or not, and we say, no, it's not continuous because, let's see what we answer. We know the answer is no, so it's got to be either A or C. No, f of x is not continuous at 4 because the limit does not exist. That's true. Let's see what this one says. This one says f of 4 is undefined. It's not undefined. F of 4 equals 7, but the limit doesn't exist. So that's why this is the correct answer, A. This gets into when you want to check for continuity. If you want to check for continuity at a point, like in this case, we're checking for the continuity at x equals 4. You say, does the function, when x is equal to 4, does it equal to the limit is the limit and the actual value of the function the same? And in this case, they're not. Because this one, the limit is undefined. And here, this is actually 7. Number 8 looks like a sort of a story problem. When I look here, this looks like a difference quotient. So mainly looks like algebra here, function notation. This is going to be sort of messy because it's 0.03x squared plus 0.47x plus 6.82. Where x is a number of people after 1991. So this is the kind of problem we're looking at. In this case, it's the price of a ticket, and we're looking at how it changes as the years go on. And they first began monitoring it or checking it in 1991. So what happens is, like 1991 is where the clock starts. So normally, they call that x equals 0. And then x is every year after 1991. So here, when they say P of 5, they're basically saying, plug in 5 for x, and we're going to calculate the price of a ticket 5 years later. So this would be like the price of the tickets for 1996. Now it's a little bit of a pain because I have to plug in 5 in for X and then do this calculation. And because these numbers are decimals, I actually need to get out my calculator. I have a pretty old calculator. As you can see here. So I'm going to put a 5 in here. Well, I know 5 squared is 25. So 25 times 0.03 equals. Now this is point. See, I have to keep track of these on my calculator because my calculator is pretty old. So 5 times 0.47 is 2.35. And then 6.82. So 6.82 plus 2.35 plus 0.75 is going to be the answer to the first part. 9.92. I'm going to check this answer because I don't want to make a math error. That's actually correct. 9.92. Now I got to do the same thing, except I got to plug in 15 for X. So 15 squared times 0.03. It's like 6.75. And then 15 times 0.47. 7.05. Plus 6.82. So if I add these up, $20.62. Also is correct. I'm just checking. So basically this is saying this is going to be the ticket. You know, the ticket price during year 0, you plug in 0 for X, it's 6.82, $6.82. After 5 years, it went from 682 to 992. After 15 years, look at it, jumped up to over $20. So ticket price is definitely going up. Look at part C, P of 15 minus P of 5. This is saying, what's the difference in the price of the tickets after 15 years compared to after 5 years? So it seems to say 20.62 minus 9.92. I want to do that in my head. I might mess up with these decimals. 10.7. So it's gone up $10.07 from year 5 to year 15. And now they say, okay, this is like the difference quotient, which you can think of this as like a rate of change number. The rate of change is how much has something changed divided by how many years have passed. So we know it changed $10.7 over 10 years. So 10.7 divided by 10 is 1.07. So it's almost like dollars per year. So this is an estimate of how much it's going up every year. So between year 5 and year 15, assuming it changes the same amount every year, it goes up at like $1.07 every year. Now, based upon that, they want you to figure out which of these statements is true. Which of the following is the appropriate interpretation of this rule? So like I said, basically we're saying every year the ticket price has increased $1.07. So this is like an average rate of change. On the average, how much is it change per year? This amount was the average price difference of a baseball ticket from 96 to 2006. I think that might be correct. Let's read the rest. From 1996 to 2006, the price of baseball tickets increased by this amount per year. We don't know that that's true. It doesn't always increase the exact same amount. So I don't think B is true. From 1996 to 2006, the average price for a ticket increased on average by this amount. the average price for a ticket. And then the result tells us the price. So this one's a little crazy, but actually C is correct. The average price for a ticket increased on average by this amount. Not gonna take time to explain this, but this is like an estimate of how much it goes up per year. It's not exact because every year is different, but this is just our best estimate. All right, let's get moving on, just because we don't want to spend too much time. Number 9, find the equation of the line tangent to the graph. Okay, I don't have time to teach this, right? You should already know how to do this. So here's a function, here's a point. Here's the point slope equation, right? If you're given a point, so this is the equation of a line. And it's where you know the slope of the line and you know one point on that line. So here's the point. So x1 is going to be 2, y1 is going to be 16. What I need to figure out is the slope of this function at that point. The way you find the slope of something is to take the first derivative. So now this is sort of skipping ahead because now you know how to take the derivative of this. I'm going to do it the quick and easy way, right? Derivative of 2x cubed is 6x squared. What I need to figure out is, so this sort of equals the slope, but I need to see what the slope is when x is 2. So I plug in 2. 4 times 6 is 24. So now I can basically take my point slope. I know y minus 16. My slope is 24. X minus 2. I'm going to multiply out the parentheses, get y by itself. That's going to be my final answer. So it's going to be 24x. So 24 times -2 is -48. I'm going to add 16 to this side. So I think should be 24x minus 32 if I did not mess up on the math in my head. So that's the equation of the tangent line at that point. All right, let's do a couple more, then we'll maybe stop this video and start a new one. Number 10, list the points in the graph and interval from 0 to 5 at which the function is not differentiable. So function differentiable, you got to check for 2 things. You can't have any gaps or breaks in the graph, and you can't have any like sharp corners. So any corners or any breaks in the graph, it's not differentiable. So here, x is 0 to 5 or 5. So we're basically looking at this whole graph here. And we're saying, what are the values of x where this thing is not differentiable? So we're okay here. It's a nice graph. It's smooth. But look, at you get to here, you got a point or you got like a corner, which means we cannot find the derivative when you have like a point or a corner. So far, x equals 2 is a problem. Now we go up here, we got a gap, because right here when x is 3, the function jumps down here, then it comes back up. So definitely when x is 3, we got a problem. So now we keep going and we're okay until we get here, and then we got a big jump again, a big gap. So when x is equals 4 is a problem. And then here we go straight and we're okay. So it looks like there are 2 places here where this function is not differentiable when x is 2, 3, or 4. And that's correct. Now let's just do one more similar kind of problem. and then we'll take a break. Number 11 is another graph, same question. Where is it not differentiable? So we're looking for gaps or breaks in the graph and points or corners in the graph. So we go along here. So here it gives us these specific places for us to look. Here at x equals 0, it's perfectly fine, no breaks, gaps. But when you get to here, x1, what happens here? We have the big break or big gap. So x1. Now here, just so you know, they're supposed to list all the possibilities here, but it didn't print it correctly. So let me just list the ones where it's not differentiable. So x1, it's not differentiable. Now you go up here, x2, what's happening here? The function doesn't exist. There's a gap, there's a break. So x2, it's not differentiable. Go down here. Here is like a corner or a point, which we cannot have. So x3. You go back up here. What's here? Another gap, another break. x4. And then at x5, actually everything's okay. So of these 6 places to look here, 4 of them, the function is not differentiable. All right, now we're ready for problem 12. Now we're going to actually start figuring out derivatives. Now's a good time to sort of take a break. And the next video we'll pick up here with problem 12.